So in the meantime, I will just talk about QRST for those that never heard about it. So this is a series of seminars organized by the Matter Lab group from Alana Spurguzi group at University of Toronto and Zapata Computing. And we are also part of the CQIQC in Toronto. So this is a short talk seminar. So we'll have two talks, the first one from Patrick Coles and the second one from Russ Duncan. We will record everything, so we are now recording the video of the talks, and we will upload them in the YouTube channel together with the speaker slides and the chat history. So both talks are 25, 30 minutes each one. So if you have questions at the end of the talk, you can ask whatever you want, either in the chat or just unmute yourself and talk. And if we run out of time, we normally stay a little bit longer after the two meetings, so we can continue the discussions with the speakers a little longer, okay? So if you have any questions, please let us know in the chat and we will answer them. And I think we can start, right?
Yeah, I wanted to add one thing. So often, like, a lot of good discussion is happening in the chat. So actually, if someone is watching this on YouTube, I really recommend also checking out chat history, because there are some great questions and great answers there. So it gives you additional context.
Especially many papers that are shared.
Oh yeah, and many good reference papers.
Yeah,
that's true.
Okay, so let me introduce you Patrick Coles from Los Alamos National Laboratory in USA. He currently leads the near-term quantum computing group there, and he focuses on fundamental issues related to quantum machine learning and noisy quantum devices. He also organizes the great summer school in Los Alamos each year. And previously, he did a postdoc at University of Waterloo and National University of Singapore and Carnegie Mellon University, and received his PhD at University of California, Berkeley. He has a broad background that includes prior work in quantum cryptography, quantum information theory, quantum foundations, and quantum matter physics. And he will present us the Barren Plateau problem, in particular it's titled Barren Plateau Landscapes in Variational Quantum Algorithms, which is a very important problem in variational algorithms. So the floor is yours. Welcome, Patrice, and thanks for your collaboration with us.
Yeah, thank you so much for inviting me to this wonderful seminar series. So I'm going to now share my content. Let's see, so is it, whoops, there it is, found it. Okay, so can you let me know if you see my slides?
Yeah, we can see it.
You can see this? Okay, great. Yeah, so Barren Plateau Landscapes and Variational Quantum Algorithms is the topic of today's talk. And, you know, just a sort of spoiler alert, there's sort of three different landscapes that I'll be highlighting. One is trainable landscapes. The other one are landscapes that have a barren plateau due to lack of knowledge or ignorance. And the last one is barren plateaus due to noise. So before we get into that, I need to first introduce, let's see if the slides are going, it'll take some time, okay. I need to first introduce variational quantum algorithms. So there's an exciting paradigm for near-term quantum computing where the idea is that you have a parameterized quantum circuit that you train to accomplish some task for you. You have an input state row, an ansatz, and then you do some measurement of a cost function. You then use a classical optimizer to optimize that cost function where the parameters are parameters inside the gate sequence here. And everything here can be made problem specific, the input state, the ansatz, the optimizer, and the cost function. So really the algorithm comes in terms of the details of how you choose these different components. But this is the basic structure of variational quantum algorithms that many of you are already familiar with. So why is it that we're interested in variational quantum algorithms? Or at least personally, I can state the following reasons. There's very few strategies that are known for constructing quantum algorithms, basic building blocks like quantum field, sorry, not quantum field theory, quantum Fourier transform. And there's also, quantum algorithms are non-intuitive to the human brain. And this is even more true for when you have connectivity issues or native gate sets. Furthermore, when you have noise, it's non-intuitive how to avoid noise. And variational algorithms provide natural means for error mitigation. But for me, the most compelling reason is that variational quantum algorithms are the natural quantum analog of classical neural networks, and these have revolutionized.
Sorry, Patrick, sorry to interrupt you, but we don't see the full slide.
You don't see the full slide.
It's cut somehow.
It's okay?
Yeah, it's okay.
Yeah, it's okay.
Okay, great. Thank you.
Go ahead.
So, yeah, so for me, the most compelling reason why, why variational quantum algorithms are interesting is that they're the natural quantum analog of classical neural networks, and these have revolutionized classical computing. So the question is, will VQAs do the same for quantum computing? And there's many applications that, of course, such as electronic and nuclear structure and the variational quantum eigensolver, dynamical simulation. So this is a plot showing that you can actually simulate for longer times with higher fidelities than traunerization using variational quantum algorithms for dynamical simulation, solving combinatorial optimization problems, and solving linear systems of equations. And there's even more applications beyond that. But the key question about variational quantum algorithms is how will they scale? And how will they scale to large problem sizes? And to answer this question, heuristics, numerical heuristics will play a crucial role. And this is certainly a good line of research to do numerical heuristics. And just as an example, for our linear systems variational algorithm, we do numerical heuristics where we show that the time to solution for a specific problem scales linearly in the number of qubits, and for random sparse problems goes as a power law with a number of qubits. And this is, of course, exponential improvement over what you would have classically. So on the one hand, heuristics are going to be absolutely crucial for understanding the scaling of variational algorithms, but still they leave something to be desired, because we would really like to have analytical sort of general results. So the question is, can we actually derive analytical scaling results for variational algorithms? And the answer is, to some degree, yes. We can study in particular the question of how does the gradient scale with problem size. And the first paper to do that was this paper by the Google group called Barren Plateaus and Quantum Neural Network Training Landscapes. And they considered this setting where you have an ansatz, U of theta, and you have a particular parameter, say theta sub k, that you want to consider the partial derivative with respect to. And so you want to consider this derivative with respect to theta k, and maybe that's somewhere in the middle of your ansatz. And they basically said that if you can guarantee that either the portion of the ansatz to the left, which is u minus, or the portion of the ansatz to the right of that gate forms a two design, if either of those statements is true, then you can show that the variance of the gradient vanishes exponentially in the number of qubits. And because the first moment of the gradient, first moment of the partial derivative vanishes or is equal to 0, then that means that the gradient is exponentially concentrating because its variance is being suppressed. It's concentrating around the value of 0 as you increase the number of qubits. So, right, and what that corresponds to in terms of the landscape is it basically looks like this picture down here, where it's a statement, it's a probabilistic statement basically. It says that if you randomly pick a point on your landscape, then with very high probability, you're going to be in this flat region. There are other points on the landscape that aren't flat and do have a high derivative, but with high probability, you're not going to be in that region. You're much more likely to be in this region that's flat. So, so this sort of a two design assumption seems abstract, but it turns out you can connect it to real ansatzes that people are interested in. There's this idea of a hardware efficient ansatz where you use the local connectivity of the hardware to construct a sort of nearest neighbor ansatz. And it was shown in the literature that if the depth of that ansatz is deep enough, namely if it's polynomial in the number of qubits, that that ansatz becomes a two design. So this hardware efficient ansatz with local connectivity actually becomes a two design and satisfies the assumption of the theorem. And hence this is this isn't just sort of an abstract theorem, it actually applies to real ansatz that people are interested in. So that's the background on the literature of Barren plateaus and variational algorithms. And then, our group came along and asked the question, can we extend the Barren plateau result to shallow depth? Because previously, this statement was basically for sort of deep ansatzes. And it turns out we found the answer is yes, if we allow the Barren plateau phenomenon to extend, to depend on the cost function. Here's our paper called Cost Function Dependent Barren Plateaus in Shallow Quantum Neural Networks. And just to give some intuition for how it could be cost function dependent, you can consider a toy model problem where your goal is to try to prepare the zero state from the zero state. So you're just trying to learn the identity gate. And there, your cost function, if you want to make what we call a global cost function, you would just basically penalize yourself for being orthogonal to the zero state. So you're just looking at the overlap with the projector orthogonal to the zero state. That's a very natural cost function to consider. However, if you do that, you end up with landscapes that look like this on the left-hand side, where this blue landscape is for a small number of qubits, and then as you increase the number of qubits, you get to this orange landscape where the valley containing the global minimum narrows. We actually call that something else. We call it the narrow gorge phenomenon, but it's closely related to the Barren Plateau phenomenon. And furthermore, this other portion of the landscape becomes exponentially flat. In contrast, if you look at, and these are actually two-dimensional cross-sections through the landscape, but if you look at a local cost function where you penalize yourself for being locally orthogonal on each individual qubit, you end up with a landscape that looks like this, which is actually trainable. And you can see also that if you randomly pick points, which are these black dots, then for the local cost, you have a very high probability of actually being in the valley containing the global minimum, whereas for the global cost, you have a high probability of just being up in this top part, which is flat. So that's sort of the idea of how it could be cost function dependent. And then we formalize that by defining some general notion of a global cost function and a local cost function where it's defined in terms of the observable that you measure, O, at the very end. And we consider this sort of, once again, this block-like structure where each block forms a local 2 design. And our main results are that if you do have this global cost function, the variance of the gradient vanishes exponentially in the number of qubits, so long as the depth L is polylog n. So this is actually shallow depth. And conversely, the local cost function has a only at worst polynomially vanishing gradient as long as the depth is O log n. And right. So that can sort of be showed diagrammatically with this diagram where red means you have a Barren plateau, you have an exponentially vanishing gradient. Green means you have a polynomial vanishing gradient, and yellow means you're sort of in between polynomial and exponential. And so this sort of summarizes our main results, showing that for shallow depth, we prove that global cost functions have a Barren plateau. You can then combine that with the Google result to then extend that out to poly n. And so then this sort of gives the complete picture, combining our results with the Google result. And so then we can see for global cost function, the situation is fairly hopeless, whereas for local cost functions, we see that there is actually a trainable region for shallow depth. So that's our main results from an analytical perspective. We also illustrated this numerically, for this algorithm called quantum autoencoders, which was introduced by the Zapata team. And what we found, sort of agrees with the theory, which is that if you use a global cost function, it trains for small numbers of qubits, but then once you get sort of beyond 20 qubits, then you just see we get a flat line all the way up to 100 qubits. Whereas for the local cost function, very nicely, it actually trains all the way up to 100 qubits, which is the largest number of qubits that we considered. So you can see that local cost functions provide a strategy to avoid this Barren Plateau phenomenon. And we've recently extended this result beyond sort of the hardware efficient ansatz paradigm to actually perceptron-based quantum neural networks. I just mentioned that we observe similar behavior with a cost function dependent Barren Plateau in these sort of quantum neural network situations where you actually have training data. And we've also extended it to different cost functions relevant to dynamical simulation, where you want to diagonalize the Hamiltonian, we found that when we formulated a variational algorithm for Hamiltonian diagonalization, that it turns out you can actually train this cost function as long as the Hamiltonian is local. So there seems to be a connection between locality and trainability. And I did want to emphasize the point that, some people say that, well, polynomial vanishing gradients are still vanishing, but you can always compensate for that with polynomial overhead, which is ultimately the goal of quantum algorithms, right? So quantum algorithms, the main goal is to try to get exponential speed up. But as soon as you have an exponentially vanishing gradient, then you have to compensate that with an exponentially large number of shots. So this is really, so Barren plateaus really are a complexity theory statement to say that your algorithm has exponential scaling if you have a Barren plateau, because you have to use an exponentially large number of shots to in order to make progress. Okay, so that summarizes the first part of the talk on noise-free Barren plateaus. Oops, sorry, there's actually one more remark, which is that there was recent work by the Moscow group that basically highlighted the fact that in the context of VQE, this Barren plateau phenomenon or trainability phenomenon actually shows up when choosing the fermion to qubit mapping. So our work actually has implications for whether you want to choose, say, Jordan-Wigner or Bravais-Kitaev in terms of, because these lead to different localities of your cost function. Okay, moving on to the noise-induced Barren plateaus. We very recently had a paper out. This was a collaboration also with two of our summer students, Samson Wang and Enrico Fontana, who actually were summer students in our summer school. And the setting that we considered there was pretty generic. It's actually more generic than what we considered in our previous work, because we didn't actually say that you needed a hardware efficient ansatz or anything. We just considered a general ansatz that consisted of a layered structure. So this would apply to unitary coupled cluster ansatz, as well as the quantum alternating operator ansatz. And so it's a generic ansatz, and we just assumed that the noise acts before and after each layer, and the noise is local. So we assume that the noise on each qubit is a local channel. In particular, we assume it's a local polychannel, which includes a special case of local depolarizing noise where the Bloch sphere shrinks symmetrically, but you could also have asymmetric shrinking along the three axes of the Bloch sphere. And the noise parameter, and the key noise parameter that shows up in our results it's called Q, and this is basically the noise along the sort of least noisy axis. So if the z-axis happens to be the least noisy, then Q would be the noise, the sort of shrinking factor along that axis. Okay, so that's the setting of our analysis. And then, so our main result here is now that the partial derivative of the cost function is exponentially vanishing again in the number of qubits, provided that a condition is satisfied. So this particular condition appears down here. And what is this condition? Well, it's a statement on the circuit depth L. L here is the depth of the quantum circuit. And it says that as long as the depth of the circuit grows quickly enough with the number of qubits, then this is satisfied. What does quickly enough mean? Well, here the function on the right-hand side you will see is a linear function of the number of qubits. So automatically we see that if L grows superlinearly, if it grows faster than linear in the number of qubits, then this condition will be satisfied and you'll have this noise-induced Barren plateau. On the other hand, if L happens to grow linearly with the number of qubits, then you can also satisfy this if the noise is strong enough. So if the noise Q exceeds some threshold, then actually you can also see this noise-induced Barren plateau for linear depth as well. So that's our main result. And I want to say that this, where does this result come from? Well, sort of intuitively, the idea is that it comes from the cost function concentrating around the value of the maximum state. So we have another result in the paper that sort of gives motivation for where this result comes from. And it comes from the fact that the noisy cost function C as compared to the discrepancy between the noisy cost function and the value of the noisy cost function, the value of the cost function for the maximally mixed state here is the discrepancy vanishes exponentially. So G of n here is some exponentially vanishing function. And so pictorially, what that sort of looks like is as follows. So as you increase the problem size, and and consequently increase the depth of your circuit with the problem size, then the cost function landscape is gradually flattening and flattening and flattening. And it's approaching the value for the maximum mixed state here. So that's our main result. And right, so it's an exponential flattening of the entire cost landscape. It occurs if the circuit depth is linear and the noise strength is above some threshold, or alternatively, it always happens if you have superlinear growth of the circuit depth. And we did not make any assumptions about the locality of the cost function or the parameter initialization, or really the ansatz either. So you could also ask, like, is there actually some sort of analog of this cost function dependent Barren Plateau? And we actually found some nice analog of that. And we found that if you use a global cost function, basically things get worse. So we already showed that you have this noise-induced Barren Plateau, but it turns out if you happen to use a global cost function, you actually pick up an additional factor here that suppresses things even more. And we consider the special case of measurement noise, where QM is the measurement noise parameter. And basically, W is the sort of weight of the polystring. So if you have a global cost function, then W is equal to N, the number of qubits. And so you basically get QM to the N here, an additional factor. And we like this result because it was it once again connected the locality of the cost function to Barren Plateaus, and once again, suggesting that global cost functions are not the best to use. This has implications for QAOA, quantum approximate optimization algorithm. So because in QAOA, there's sort of two issues. Basically the circuit depth grows not only with the number of rounds of qualia, but also with the compilation cost of a single round. So even if the number of rounds is constant, it turns out that we expect to get linear compilation depth just from compiling a single round. But also the number of rounds in qualia also may need to grow with the number of qubits too. So you could have two issues here associated with qualia. Also in the context of chemistry, so the unitary coupled cluster ansatz oftentimes has a depth growing polynomially in the number of qubits. So this has implications both for qualia and for VQE. We illustrated this numerically for qualia. And so first down here at the bottom, we showed that we sort of confirmed the fact that the gradient in this bottom plot here is actually decaying exponentially in the number of layers. And hence when the number of layers grows linearly or in the number of qubits, then you get the Barren Plateau. Similarly, we found the concentration of the cost function with the number of layers. We also saw the performance decaying significantly with the number of layers, in contrast to the noise-free setting, where the performance actually gets better with the number of layers. So this seems like a very important issue, especially in the context of QAOA. So just to summarize, so noise can induce Barren Plateaus if the circuit depth scales polynomially in the number of qubits. This is conceptually different from noise-free Barren Plateaus. And it actually occurs irrespective of pre-training, initialization strategies, locality of the cost function, choice of ansatz, or correlation of parameters. And I mention this because all of these strategies that actually appear in this list have been strategies that have been proposed to avoid noise-free Barren Plateaus. And so even if you manage to get past the noise-free Barren Plateau, you can still run into this noise-induced Barren Plateau. And so then the question is, well, how do we avoid this noise-induced Barren Plateau? Well, so there's the simple ideas are maybe the best ones, and that's, you either reduce your circuit depth or reduce your noise level. So this really highlights the need for better methods to reduce ansatz depth, and hence it can motivate a new sort of, or further motivate this field of research on reducing ansatz depth in variational algorithms. reducing noise level, however you can do that, maybe partial error correction, and if there's any other strategies like error mitigation, it's still unknown, I would say, at this stage, if error mitigation can solve this problem. But I would say, so finally, I would just leave you with this sort of fun slide that kind of summarizes the situation with respect to trainability. And so really it's important to consider both circuit depth and noise. And so we already know, so if you have low noise, you can still run into barren plateaus due to randomization just by increasing your circuit depth. Alternatively, you can run into barren plateaus just by increasing your noise level. So you really want to avoid this island of utter flatness, and you really want to be down here at low noise and low circuit depth if possible. So with that, I'll say thank you very much and happy to take questions.
Thanks, Patrick. I really like this final slide. It's very informative.
Yeah,
so let me check the chat because I think there are some questions here. For instance, last one was from Johannes. He said, can we account for the difference between global and local cost functions by noting that a global cost function contains some hidden exponential dependence on the number of qubits? That is the cost to map the global observable to a local one.
So what you might be referring to is the notion of like taking, say, like a global projector and putting it into, say, like the Pauli basis. But our result actually holds even whenever you formulate things in the Pauli basis. And so then I guess my answer is no to that question, because I'm sorry, it's taking me a while to get back to the slide. But because whenever we actually formulate this result, these operators they could be projectors, but they could actually be Pauli operators already. And so in that sense, well, I'm not sure I've understood your question, but if your question was, what happens if you take, like, say, like a projector and transform it into the Pauli basis, then my answer to that is no, because we actually formulated this also for the Pauli basis. Or was that what you're asking, or were you asking something different?
Yeah, I mean, this was more of a hunch in a way. So because I was thinking, if one has a global observable and then one would, preferably go to its eigenbasis, and then this transformation would probably be very costly. And then, I mean, it was just a thought I had when reading the paper, and that there might be some hidden exponential dependence, because I mean, it would beautifully explain the scaling at least.
Yeah, so we're not aware of that hidden exponential dependence, and we did, like I said, we did when we first posted our paper. Someone asked the question. Actually, Jacob Biamonte asked us the question of whether this hidden exponential dependence would show up if you transform, say, like a global projector into the Pauli basis. Because you can imagine just taking like the all zero projector and then decomposing into the Pauli basis, then you have an exponential number of terms. But then we pushed back and basically said that we can also formulate this when your cost function is already in the Pauli basis, so you don't have that exponential overhead. So yeah.
Okay, thanks.
Yep.
Okay, another question from Gidong. He asks, how to determine a cost operator is global or local if the form of the cost is not clear? For instance, the cost function of max cut, is it global or local, and why? And he also gave other examples. If the operator owes the projector of an unknown state, and if the cost function is data driven, for instance, given by a training data set, or if the operator is cost function of some of Z operator, I guess.
Yeah, so I believe well, I mean, maybe it depends also on the locality of the graph itself in max cut, but I believe typically it is local. And what was the second part of the question?
I think the main question is, the cost function of max cut, is it global or local, and why? Yeah.
So I believe it's local for typically. Off the top of my head, it might actually depend on the nature of the graph, but I think in practice it typically tends to be local if you have, say, local graphs. But let me also think about that and get back to you. Yeah, I mean, but the question of how do you know whether it's global or local, is basically whether it sort of fits into this form or this form, I guess. And it depends on like how many, like it's sort of like many bodiness, how many non-trivial operators do you have here in this sort of product? How many of these are identities versus how many of them are, yeah, non-identities?
Okay, so I think that that's everything from now. So if anyone has more questions, you can just wait until the end of the next talk, or just ask in the chat, and probably Patrick can answer in the chat too. Yeah. So thank you very much, Patrick, for this very interesting talk. And let's move to the next speaker.